In this module, we will cover the composite pattern. That's a pattern that takes advantage of recursion and is often used when your data resembles a tree-like structure. I'm Kevin and I'll guide you through this module. We'll start by describing the pattern using a real-life example. As real-life example, we will use a file system scenario. After that, we will map that to a structural example and will implement a real-life example in a demo. We'll continue with learning about use cases for this pattern and pattern consequences, which can be positive or negative. We will end the module by looking into related patterns. Let's continue with describing the composite pattern. The composite pattern is a structural pattern from the well-known Gang of Four design patterns. Its intent is to compose objects into tree structures to represent part-whole hierarchies. The composite pattern lets clients treat individual objects and compositions of objects uniformly, as if they all were individual objects. What would this translate to in real life? Well, composing objects into tree-like structures is something we're all very much used to. Imagine the structure of an XML document, where each element in turn consists of other elements, which can again consist of elements. Another example might be an application in which a user can draw. You can represent that as something that consists of one or more lines and potentially one or more pictures, which in turn consist of lines and pictures too, and so on. The example we're going to work with is another one you can undoubtedly immediately picture: the file system. We've essentially got items in there, let's name them file system items, that are either a file or a directory. Such a directory can consist of one or more files and or other directories, and so on. So there's our tree structure already. We've got two classes in our tree structure, a file and a directory. Now imagine we want to get the size of all the items in our tree structure. We would have to run through all these objects. We need to know the exact classes, file and directory. We need to know the method to call on them to get their size. We need to know how deep nesting goes to be able to access those levels of files and directories, and so on. This becomes very cumbersome very fast. And that's what a composite pattern helps with. What if, instead of working with directory and file classes, we'd work with a base file system item class, a common interface through which we can calculate the total size? Let's put that into practice. On the file system item base class, we define a method to calculate its size, getSize. This is implemented by our file class and by our directory class. The directory class, next to that, also stores its children and includes methods to add additional file system items, so the tree can be built. On the file class itself, we don't need that, as such a file cannot have children. Only a directory can. The other common thing we want to do is define a common operation on the file system item, a method to get the size of it. In case of a single file, implementing this is simply a matter of returning the actual size. But in case of a directory, that method would count the file size of the directory itself and then run over all file system items in its file system item collection, get the size for each and add them up. And like that it continues. That's a very nice example of recursiveness. All of this is transparent for the client. It's the file system item itself that will handle counting the size of all the items in its tree structure. This is a lot more convenient to work with. So that's our real-life example. Let's map this to the pattern structure. Our base object, that's a file system item, is what maps to a component. This can be implemented as an interface or an abstract base class. This component thus declares the interface for objects in the composition and potentially implements default behavior, which is possible if you implement it as an abstract class. It also contains a common operation. That common operation in our example was the method to get the file system item size. It can also potentially define an interface for accessing and managing its children. This was obligatory in the initial design pattern template, but in more current iterations of the pattern, this type of behavior is often defined and implemented on the composite itself instead of on the base class. We'll get to that. One item would be a leaf. In our case, that's the file class. This one does not have children. It derives from the component and it implements the common operation. So, behavior for the primitive objects in the composition is a responsibility of the leaf. Another item then would be a composite. This one also derives from the component base and it stores a set of components, children. It implements the common operations and defines operations to add or remove children. It thus defines behavior for components having children. And lastly, there's the client, of course. This one manipulates objects in the composition through the component interface. In the structure as it's detailed in the Gang of Four Design Patterns book, the component abstract base class also defines an operation to get a specific child by index. But as mentioned before, you should not see that as a literal must to have such an operation. Instead, see it as a reminder that you can add that type of functionality if you need it. In the same spirit, we have varied this a bit. In the original implementation, the add and remove operations were defined on the abstract base class and not overridden on the leaf class. We simply didn't define them on the base class and instead added them to the composite class. So this just goes to show that there's multiple ways of implementing a pattern. Just make sure you keep the intent in mind. Let's implement this with a demo. Time to implement our example. In this demo, we will implement the composite pattern using the real-life example we just described. We'll start with the abstract base class, the file system item. This is the component. We give it a name and define an abstract method on it to get its size. We also add a constructor that accepts the name, signifying we expect consumers to pass through a name when constructing the item. This is an abstract class, so it cannot be used on its own. The next step, thus, is implementing this class. Our first implementation is the leaf. In our case, that's a file. Next to a name, we also expect a size this time, so we add a constructor that accepts that size and stores it in a private field. Implementing the getSize method is then simply a matter of returning the size variable. The directory from our example is the composite. And it too derives from file system item and requires a size. So we have a likewise constructor as we had for the file. Yet we haven't implemented file system item yet. When we do that, we see that we need to provide an implementation for the getSize method. And that's a bit more complicated in this case. As the directory is a composite, it can contain other components, file system items in our case. So we need a variable to store these in. We make sure this one is initialized to avoid null reference exceptions. We also wanted to add and remove functionality. There's multiple ways of doing this. We could simply expose our private list of file system items, but I'm not a big fan of that as it breaks encapsulation. It would allow other classes to directly manipulate this list. Whether or not you want to do that depends on how much your use case requires you to shield this list. For our case, we're gonna make encapsulation as strict as possible. We actually don't need this to have a property getter and setter. So we add the two methods to add and remove file system items by manipulating the file system items list. Lastly, we can now implement the getSize operation. This shouldn't just return the size value. It should return the sum of the current size value and that of each size of each file system item. In turn, one of those could be a directory which would result in the size getting calculated by running through all of its children, and so on. So that's a very nice example of a recursive method at work. From inside of the getSize method, we call getSize on each file system item. And that's it for our implementation. Let's write a bit of code to test this. The first thing we need to do is create our tree structure. So let's already create a few directories and files. We start with the root, which we give no specific value for size. To that we want to add one file and two directories. So we new up a file and two directories. We give the file and these directories a size. And we add them to the root. We're not going to stop there. We're going to create a tree that's a bit bigger than this. So we're going to create two sub-level files as well. We new those up, giving them a size, and we add them to one of the top-level directories. Like that, we have something that is starting to resemble a nice tree hierarchy. And then let's test whether our getSize methods actually work. So we write out to the console window a getSize statement on the top-level directory 1, one on top-level directory 2, and one on the root itself, which should result in the full size of our tree. Interesting to notice here is that at level of the client we are getting the size, but as far as the client is concerned, interacting with a leaf is exactly the same as interacting with a component. We're calling getSize on the directories here, but we might as well call getSize on one of the files as well. This is completely transparent to the client. Let's give that a try. And there we go, our three getSize statements checked out nicely. And if we do the math, it seems that it indeed checks out as well. Let's have a look at the use cases for this pattern next.